Okay, we're going to talk about content distribution networks next. And this will wrap up all of the content for the first part of the lab. So you are a website and you want to distribute your website very widely. And so you don't want to be sitting there buying machines from Fry's, plugging it into your rack, plugging it in, bringing it up in order to scale to demand. So what you would want to do is you would want to find a way to automatically deploy infrastructure to service your website seamlessly. There are multiple strategies for doing so, and I'll talk about the individual strategies, and then I'll show you something like Cloud CDN, which is part of your CDN lab, which pieces all of these techniques together to provide you one service. So if you are a Netflix or your YouTube, you would use all of these techniques in conjunction to build a highly scalable website. Some strategies is basically what we do in computer science: divide and conquer. You can partition the workload. You can replicate the resources being used to serve that workload. You can distribute the resources widely that can handle the workload. And then you would want to load balance across all of the resources that you've deployed. And all of these things are going to be used to attack this problem of scalability. So some general strategies: server partitioning, DNS load balancing, virtual servers, and then I'll talk about how these things get deployed and used. So the first thing is server partitioning. And there are two kinds of ways to partition servers. One is statically. And so in the old days, you would have www, you would have mail, you would have images, you would have shopping.blah.com. And the advantages of splitting your site across multiple named properties is that you get better disk utilization. Rather than having a single machine that holds all of this content and then replicating that thing, then all of the mail content goes on the one server, all of the www content on another, so you increase disk utilization. You save on disk space. The other advantage is that cache performance. Because all of these, for example, image files are all going to the same server, your file cache performance improves. And this style of operation is coming back in spades, because this is really suited for DevOps, and it's really suited for continuous improvement, continuous deployment. And this is how people are there. If you have multiple development teams and you want them to be able to build and deploy very quickly, then what you would want to do is break up the development teams into different small projects and implement what's known as microservices. And this gives you the agility. If you're only focused on supplying one piece of functionality to an organization, you can build a small team, and then all they do is they iterate on that one thing. And this is you can do this using static partitioning of the workload onto your team. So this is definitely something that has come up more recently. The other part of this is when you deploy it, you don't have a larger website to integrate into. So websites, and you'll see this with web security, is they have a cookie policy, they have a content security policy, they have all of these site-wide things that need to be configured in order for your stuff to be secure. And if you are deploying the shopping cart part of the site, and you have to coordinate with the ad part of the site or the personalization part of the site, this kind of structure ends up slowing you down. So what you could do is you could split off the shopping site, you could split off the search engine site, and you could split off the other things. So that's basically where people are moving to with partitioning. The disadvantages of server partitioning without cloud provider support, you get lower peak capacity. So if you get a spike in shopping, like you're Amazon and all of a sudden everyone's hitting shopping and nobody's going to your mail server, you've already statically allocated it. So what you would need is some backend to automatically ramp up more servers for your shopping site. So that's why this says without cloud provider support. You also have very coarse load balancing. The load balancing is done based on the name rather than the instantaneous usage on a particular site, which is not ideal. Whereas if you had a monolithically named site, then you could spray all of the requests across all of those different sites dynamically. And then the last one is management costs. You have to figure out how all of these sites piece together. Okay. Another way to do the partitioning is dynamically. So this is, the idea here is to actively forward deploy content and then automatically write the host name of that content in your base HTML page. So the idea here is that if you have an origin server that's getting hit all the time, then what the origin server can do is it can forward deploy some of its content to, for example, the PIDIC block, and then it can assign a name to that content. Maybe it brings up a server dynamically, and it can assign the embedded links in a web page to point to these things that are locally hosted. So that's basically a content distribution function. And so this is effectively giving you this multicast based on where the client is. And this is what Akamai, AWS CloudFront, and then GCP's Cloud CDN are going to try and do. They're going to try and forward deploy and then map a new name that points to that forward deployed content for you to access. Okay, so this is an animation of what's going on with this dynamic server partitioning. So what you would do is you are here at pdx.edu. You're trying to get ESPN's site up. And so the first step would be ESPN saying, you know what, I want to be able to forward deploy content close to Portland. So say this is in the PIDIC block. They have these servers running there to be very close to Portland State. And they would forward deploy, and if you've looked around ESPN's site, you'll see stuff like akamai-tech.net. These are all of the named servers that Akamai hosts nearby to send requests rather than to the origin, to send requests down locally nearer to where the content is being accessed. So this is what they would do. They would have the base site, and then Akamai would distribute, or Akamai through ESPN would distribute content, all of the images, for example, all of the videos. They would get forward deployed into a data center in Portland, for example. And then what you would do is the host, or the client, would then go and access the base page, and the base page would dynamically have the embedded content rewritten so that it would point to the content that was forward deployed. And so in this way, you can distribute the highly accessed content to a place that's very close to the client on this side. So this is the slow internet, and then this is high-speed ISP, and then you're rewriting the embedded content so that the next request for the embedded content goes here. And you see this throughout stuff like ESPN happening. All right, are there any questions about this? What's going on? This is how Akamai started. So the advantage of this is that the network utilization is improved. Like, you don't have to go over the wide area internet to get your content. And this ends up saving you a lot of money. And this is assuming that the network bandwidth is much more expensive than storage bandwidth, which it is, and will always be probably. But this actually saves you a lot of the transit traffic fees, this is how Akamai built its business. Because people were using this and saving a ton of money on their traffic, their network ISP fees. And so by distributing a whole bunch of disks near people, they were able to take that sort of profit. You get better load distribution if the replicas are distributed based on popularity. So at the ESPN side, they can figure out what is the most heavily accessed content, and then they would dynamically forward deploy that content and not the badminton. Sorry, I don't want to pick on anyone who likes badminton, but like if it's like badminton finals, like nobody's watching, maybe I'll host that here in Connecticut. I think ESPN's in Connecticut, but then maybe yesterday's Steelers-Chargers highlights would go like, next door. The disadvantages is that you have this distributed management cost. You have the cost of integrating all of the Akamai infrastructure into your own site, which is not trivial. And moreover, you have lock-in, right? Now you're locked into Akamai as your CDN provider. Yes? think it's a dumber algorithm than that, because content's always changing. I am sure for other styles of content, then yes. Like, especially for Netflix, Netflix could probably guess that Christmas movies every 12 months are going to get hit again. So maybe I'll forward deploy that. But I think even Netflix is dynamic. Like, Netflix will also, because maybe a meme got sent around that was unpredictable, that all of a sudden spiked viewership of something or other. But I don't know actually the algorithms that are running any of these things. Okay. Another way of handling this workload is through something called DNS load balancing. And this was popularized almost immediately because when the web was deployed, there was only one website. It was NCSA's homepage, pretty much. And there was a couple others, but everyone was going to their page. And they were like, because this is where the browser was. Like, everybody was going to download a browser because that's what you needed. And NCSA, this is at University of Illinois. So everyone was going there. This is the National Supercomputer Center or something like that. And so in order to handle this load, they had to do something. And what they did was they had a fully replicated server farm. And they gave each of these servers an IP address. And then what they did was they played a DNS trick. So they ran the authoritative name server for NCSA. And they were like, let's just round robin the IP addresses in this server farm to distribute the load across all the replicas. And that's how they got the load balancing to happen. And this is the reason why when you do your DNS lab and you do a reverse lookup of Google, this is why you get 4 IP addresses. Because if one of them doesn't work, you got 3 more to try as part of it. So it's a little fault tolerance. But initially, it was done for load balancing purposes. So this is how it would work. Here you have an authoritative name server, and you say this name that everyone's trying to hit to download a browser from is these 3 IP addresses. And then here's your root server and then your pdx.edu. So I'm going to ask for the name. The name is going to get me to the root servers. The root servers eventually are going to give me to the authority. And then the authority is going to round robin one of these and say it gives me the 28. Then here I cache the name lookup, and it was a 15-minute TTL on the cached lookup. And then what would happen is everyone else in this subnet, when they asked for this DNS name, it would go to the same entry, and you would go back and hit, let's say it was .28 that you got back. So that's how it worked initially, and then you would get your content back. So it's a really simple thing to do. Really easy to implement, pretty effective. Still being done today. So those are the advantages, simple to implement, uses the existing DNS infrastructure. The disadvantages is that the load balancing is coarse, and it's done over 15-minute blocks, right? Like if I give that name out to, let's see, like IBM, it's got like 200,000 employees, and they're all hitting ncsa.edu to download a browser. Well, that's not very good load balancing. So this is you don't get this per request load balancing where you can take a request and send it to the least loaded server. So if everyone is using one, if you just got unlucky and you had a whole bunch of people going to the same server, you can't move them off of that IP address. That IP address is cached for 15 minutes at least. So you don't have very fine-grained control over the load. And you're basically beholden to the caching that's being done on the local name servers. So this is why even Akamai cranks down their TTL on their DNS lookups to something really small. And you could actually query some of the Akamai names to figure out what that TTL is using the dig tool. The other disadvantage is that you require full server replication, right? Because those things are treated equally, all of those IP addresses. The next thing is virtual servers. And the idea here is to have a large server farm that appears as a single virtual server. And then you would have a single front end that does connection routing. So there's 2 styles of what goes on. The very first instantiation of this was about 20-some years ago. This was IBM. So IBM was the technology provider for the Olympics in 1996, and this is when they were in Atlanta. And this is what they built because they knew everyone was going to hit this website. Everyone's going to go to the Olympic website to get all the results. And so this is what they built. They had a server farm here, and then they had a front-end connection, and the website IP address is just X all around. And so what they built is they had everyone hit this front end, and when this front end got a request, it would take this request and then route it, simply route the thing. So this is the TCP request, a TCP SYN packet that tried and establish a connection. And when it got this connection establishment request, it would just simply load balance this request amongst all of the backend servers on that was hosted. This was in their data center. I think it was in North Carolina or somewhere. And then this request would get routed to a machine that would handle the request. And then as a response, the response would, rather than go back through here, the response would go directly over these 4 T3s. So this is 45 megabits each. So that's pretty dinky at the time. A T3 is 45 megabits. So they had basically about 200 megabits to the internet. And the actual response would then go over this network. And the connection would basically be this circle, right? Packets going to the back end would go through here, and then packets coming back would go through here. And this is asymmetric. So you would have a much bigger pipe on the download because people are mostly downloading from the Olympic web server. They're not uploading anything. And then this could be something that was much smaller. Okay. So this, if you look at this, we saw a picture just like this before. This is similar to what we did with the NAT devices, the network address translation devices. So there you had a bunch of backends, and as they were going to and from the internet, they were basically being routed, right? So this is actually the reverse operation. So remember when we talked about NAT, that we had a hard time going through a NAT to any one of the backend servers? Well, in this case, this thing is doing a reverse NAT. It's saying, I'm going to take this packet to a single IP address, and I'm going to rewrite it to one of the 4 backend servers. So that's what they call this. They call this front end a reverse NAT. All it's doing is rewriting the connections that go through it. And then on the other side, it doesn't need to touch the data. And it doesn't need to touch the data because this is actually using the IP address of X. It's like you put a big circle around this whole thing and put that as one machine. It's very similar to a NAT, where you put a circle around the NAT, and then that's one machine to the internet. The same idea. Okay. So there is some management here. TCP, like you're doing the exact same thing as a NAT device would do, is store a mapping, and then just use that mapping to forward subsequent requests. So I'm not going to get into the details of this. It's there if you're interested in. Okay, so advantages of this approach is that there's very minimal packet rewriting going on. Only those packets on that forward path are being rewritten. And it's much more reactive, right? I don't have a DNS timeout to manage my load. I can actually manage the load immediately upon getting this connection. If I have some back channel that says the uptime of these 2 things are at 100% and then these things are at 0, I can immediately do the route to the underloaded servers. I don't have to wait for DNS entries to get updated. Okay. Some disadvantages, potential non-stickiness between requests. So if I have a shopping cart and I'm expecting to go back to the same server to handle my shopping cart state, like if you spray me to some other server, like say I start on this server and then all of a sudden this thing, my subsequent request goes over here, I'm not going to be very happy because I have to do another SSL handshake, right? Because all that stuff got blown away because it was a different machine that I'm talking to. So you have this cache performance versus partition servers where you can get that same session over and over again. So that's one big disadvantage of this approach. Okay, so this was eventually built into a lot of networking gear. So in the late 90s and the early 2000s, we got really good at building these hardware switches that did this reverse NAT operation, where you could hang off this switch a whole bunch of servers, and then it would export a single IP address that would reverse NAT into it. And so this is a lot of what's functionally going on in the cloud. When I want to, and you'll do this in your lab, I want to be able to ramp up a whole bunch of servers based on demand. And what's happening is that it's the same IP address that you're getting, but then it's just tacking on more machines on the back end to meet that load. Okay. In terms of load balancing algorithms, these switches could do a lot. They could be configured to do a lot of different things. You could load balance on the connection ID. So if you really want stickiness between SSL connections, you could actually force particular clients to particular backends. You could also do it based on server load. So you can measure the number of connections to each one of these backends, and then you could basically select the one that had the least number of them. You could go by response time. You could go by uptime on the server. You could do any number of these load balancing operations. Okay. You can also do what's known as a reverse proxy. So this is a little bit different than a reverse NAT. A reverse proxy is actually going to terminate the connection and pretend to be the server for a little while. And the reason why you would do this is because, hey, you know what? If I actually pretend to be the web server temporarily, and I get the URL, and I get maybe your SSL session, or I get your cookies, I can actually route you based on the content, on who you are. And so this is what a reverse proxy does versus a reverse NAT. A reverse NAT is going to make that decision immediately. It's not going to try and terminate the connection. But a reverse proxy will terminate the connection, and then it will forward back and forth the requests and the responses afterwards. So an example of this is Nginx. All of Google's front-end stuff is doing a reverse proxy. They're actually terminating the connection and then routing you to a service on the back end. Cloudflare is doing this. I'll give you an example of how Cloudflare is doing this in a couple of slides, and many other hardware switches. So this is happening all over the place. You're getting your connection terminated, it's pulling in some content, and then based on that, it's going to send you somewhere else in the cloud. Okay. All right. So this is the way it looks. This is how it operates in an animation. So we call this an L5 switch. So here you have in the middle your L5 switch. It's got some virtual IP address X, and then it's proxying for the real servers on the back end, IP address Y. And the client knows about X, so it connects up to X. And then the switch is going to proxy the connection. It's going to say, yeah, that's me. I establish the connection. I pull the request in. And as soon as I have the request, I can be like, okay, I know where this goes. And so I'll basically route the request. And so I'll create another connection to the actual server to handle this request. And then what I'll do is I'll just replay this request. And then on subsequent interactions, all I do is rewrite the response so that it goes back to this client, and then the same the other way. So this is what a reverse proxy is doing on the back end for a cloud deployment. Questions about that? Oh, what? It is a man-in-the-middle attack. We'll get to that. Yes. Oh, that's a really good question. Yeah, I'll get to that too, because Cloudflare is asking to terminate the SSL connection. Yes. Yes, it could mean I might need that certificate that you hold dear to be able to proxy this, right? To proxy an HTTPS connection, I would need the certificate. So yeah, that's an issue. But those are really good questions. So yeah, it looks sketchy. It is sketchy. So the advantages of this is that it increases your effective cache size again. So now you can actually do some affinity. So if I'm going for cat images, I can just send you to the server that's been handling the cat images for the last week versus spraying you all over the place. It allows for session persistence. So one of the load balancing features that you could turn on is like switch based on your SSL session ID or based on your cookie, like the first couple of bytes of your cookie, and I'll just send all of those people to a particular server so that they don't have to log back in and they don't have to do any of these other things. You can support user-level service differentiation this way. So if you've been bombing me with a bunch of requests, I'm going to proxy your connection, figure out who you are, and then I'll be like, I'm going to drop you because you've hit me 1,000 times with the same request. So you could do that, which is what Cloudflare is trying to do, right? Like that's what their business model is, to do stuff like denial of service prevention. But you have some disadvantages. There's some hotspots, and then there's basically overhead, where you're basically doing all of this at line speed. All this rewriting happening is kind of resource intensive. I want to put this in here because there's other ways of getting session persistence without having to do this. And this is what you'll see in AWS. This is an architecture that, a graph that they'll show you. And the way they do this is to have all your front ends, so this is your front end, have all your front ends share a enormous in-memory database. So this is what a Redis or a Memcached would do. This is just key value stores that are stored all in memory. Because the last thing you want to do is store any of this state, session state, in a disk that actually has to spin in order for you to get the context back. So what you would do is you would federate a cluster of machines, and within these machines, all of their RAM is basically key value stores for storing cookie state or session state. And then you would have every single server in the web tier query this central in-memory database to restore the state. So then you can spray requests all throughout the web tier, and then the web tier would just query the in-memory cache to get that state. And then similarly, you can use in-memory caches for database queries, for application acceleration. So the caching, in-memory caches, can be placed anywhere in your cloud application to speed up performance. What I'm just showing you here is that you could do it right at the web tier to make sure that your session state with that user can be retrieved quickly, because that's what you'll want to do. Because if the initial server that the client goes to is really busy, you want that other server to be able to restore that client state. Okay, this is so the service. So the branded service on AWS is called Elasticache, and then Google's, I forgot what Google, I think it's Memory Store. Cloud Memory Store is Google's in-memory database, and that's what that is what they're used for. If you see those in the product listing. Okay, we'll put all this together. Here is a fictional figure of how Yahoo used to work. I don't know. It's probably nothing. It's similar to this, but it's not. The details might be different. So here you are, pdx.edu. Here you have your Akamai forward deployed content. Here you have some explicitly named servers. So this is an image server. So Yahoo used to distribute all their thumbnails and all their article images in a single server called us.yimage.com. Here you have the name servers for Yahoo, and you got a collection of these. These things point to virtual servers that might be back-ended by a whole bunch of real servers. And so what you would have for a single site, www.yahoo.com, you would have a person go and look up the name. You would get a collection of names that you would then round robin. You would pick a name. So there it is, and you would go to that. So say you got .68, you would go here, and then within this cluster, you would get a single server to process your request. And as part of this server, it would rewrite the URLs for the embedded images, and the embedded images could either go to the statically named server. So say if it's not a popular image, it would go to here. But if it was a really popular image that got forward deployed ahead of time, then you would basically go to the local cache. And in this manner, you can get a website that performs very quickly. And so when they do these, so there's this performance test where they point the test to a whole bunch of popular websites, and they say, who's got the fastest website and who's got the slowest? If you want the fastest website, you have to do all of this kind of stuff, right? You have to forward deploy, you have to, get your DNS working. All of this stuff has to be done in order for you to compete on because there's some measurement on the milliseconds versus the percent drop-off in user attention, and it goes fast. Like, I think we have the patience of like 100 milliseconds or something, and it goes off a cliff. So every millisecond counts, which is why you would go to the trouble of architecting your application in the cloud so that it's very low latency. Okay, so there is support for all of this stuff on the cloud. GCP has Cloud DNS. AWS has Route 53 to do the name part of this thing. The other part is GCP has Cloud Load Balancer. AWS has Elastic Load Balancer. And both of these support any of these server-based load balancing, content-based load balancing, geographic-based load balancing. And this is going to be part of your lab. You'll see You'll be doing a deployment that does some load balancing and does some replication automatically. And then GCP has Cloud CDN and AWS has CloudFront. This is for forward deploying your content to servers that are near your client, to near where the content is being accessed. So these are the services that they provide. So all of these things you'll be able to get your hands on with the CDN lab. Okay, so now I want to talk about CDNs for DDoS protection. They're a little bit different. And this is what Cloudflare does. So we have a DDoS problem. We have people putting stuff on the internet with basically default passwords. And so they're getting owned pretty hard. So this is a 9 million cameras that are basically open for people to log into and then use as sources to basically launch denial of service attacks. And so now, when you have a popular website, you have to buy protection against people like these who are going to point their cameras at your site and then take you down. And so this is what has happened for things like Krebs on Security as a security blog. And the people were really unhappy with him for basically doxing all their stuff. Like, this is their way of life, and Krebs has a history of just taking people's nefarious ways of life and then taking it away from them. So he's a huge target. GitHub was a huge target. And so if you look at the DDoS attack evolution, the amount of resources available to launch a DDoS attack has just gone way up because people are just deploying stuff left, right, and center. So we have to do something about this. And so one of the things that CDNs are being used for is to do DDoS mitigation. You have access points all throughout the world. The idea is to stop the malicious traffic before it ever hits your origin. And that's what this is about. So you point your DNS to all of your forward deployed nodes, say those are my sites all around the world, and then you push out the requests, the unwanted requests out to the edge. So this is going to do a reverse proxy. You're going to do the handshake, you're going to get the request, you're going to see who it's from, and then you're going to decide whether or not to process that or drop it. So that's what's going on, and it's using the exact same mechanism I just showed you earlier. So you can drop your Mirai traffic, your GitHub traffic, your this Dyn DNS was that was pointed at Krebs actually, I think. And you can also drop these malicious requests. So in web security, there are specific commands that you know are up to no good. Like there are a bunch of SQL injection. It's really easy to spot a SQL injection attack. Like if I reverse proxy a connection and I see a SQL injection string going through, I can just drop that. And so that's what these WAFs are doing. This is web application firewalls. Let's just proxy the connections everywhere in the edge and then just see what we get, what kind of payloads we get. And then we can drop SQL injection, we can drop cross-site scripting payloads, we can drop all the known exploits at the edge before they hit your backend. Okay, so Cloudflare, Akamai, Google, and Microsoft are all doing this now. And Google is doing this for free for all of the anti-hacking sites. So now Krebs is protected by Google using this technique. This is the general architecture. So this is the way it used to be, where everybody has access to they call it your naked website over here. And then this is what you want to have happen. You want forward deploy on the edge. You want the connections to be proxied, for example, at the PIDIC block. And then based on the results of that proxy, you're going to forward deploy to, or you're going to forward that request to the actual content server. Okay, so Azure is building this in. This is from last year. They build in DDoS prevention per IP address. They do the WAF. They look at protocol attacks, and then you can just add this to your cloud project. So this used to be a huge engineering feat. Now it's just like a checkbox, which is the way things happen in the cloud, actually. So this is what they're doing, and this is the nice figure that they produced, where all of this stuff, all the customers go through, and then the attacker will eventually, the customers go through, and then this is on the edge of filtering out the attacker. Okay, so the issue with this, and this was referred to earlier, is that you have to proxy an HTTPS connection at the edge in order for this to work on those connections. And we talked about HTTPS being end-to-end security. And in order for you to proxy that, you need the private key of the web server forward deployed in order to terminate the HTTPS connection. So the private key associated with the certificate has to be used to decrypt the key from the client to do that proxy connection. But most sites, they don't want to give their private key to Cloudflare, right? This is you as an organization. These are your crown jewels. And so this breaks the end-to-end security guarantees of TLS. So yeah, choose your poison. Do you want the protection, or do you want to trust Cloudflare with all of your secret? Well, your main secret is basically what you're providing. And so you have this trade-off of resilience against DDoS and application security. So this is one of the things that they developed at Cloudflare. This is a keyless SSL, where all of you web servers would co-locate a key server at the edge. So then Cloudflare will ask you to decrypt a key that's been encrypted with your private key, and then this would be used to terminate the connection. So then if you have a presence in Cloudflare CDN that will be able to decrypt that certificate, you can proxy the connection there. But this gets exactly to understanding what is going on with these keys to understand why this thing has to be done this way. Because otherwise you'll look at this and be like, I don't get a thing. I don't understand any of it, but if you realize that you need to be able to decrypt this to terminate the HTTPS, then you realize you actually need the private key of the web server to be sitting right next to them there. So that is it. And we will start with the web stuff next class.